Welcome back to Chapter 7, our final unit of the chapter, Unit 4. We're going to look at Section 3 today. Our learning targets, you can see them posted here. These are your goals for today. Hopefully you can say at the end of the lesson, I can graph exponential equations with base E. I can use exponent properties to simplify expressions with base E. And I can use A equals PE R to the R times C, excuse me, to calculate continuous interest. Have those down and ready for your notes tomorrow. Okay, what is E? E is called Euler's number. E-U-L-E-R, it's pronounced Euler. O-I-L, Euler's number. Okay, here's some notation for it. E equals 1 plus 1 over n to the nth power as n approaches infinity. Positive infinity, talked about approaching positive infinity and limits before. E equals the limit of n as n approaches infinity of 1 plus 1 over n to the nth power. Okay, this is a rate of calculus. Bottom line is just a number. E equals 2.71828. In your calculator, if you get your calculator out, the E button, if we go down here, let's go this thing out. Second ln, that's e to a power, so we could do e squared, e the first power. Also just plain old e, if you get second divide, that gives you plain old e. So here is e approximated a little bit further. Okay, but bottom line, it is just a number, it's like pi. Okay? Couple things as we get going. We talked about growth and decay before. What is growth going to look like when we're graphing? If we have a growth function with e, it's going to be f of x equals e to the positive x. If I have a decay function, it's f of x equals e to the negative x in general. And so let's keep that in mind as we go forward to the next slide. Graphing e functions. I have two functions. F of x equals 2e to the x, and f of x equals e to the negative 2x. Which of these is growth and which of these are decay? Well, if we look at the one on the left here, f of x equals 2e to the x, the power of x is positive. So this is a growth function because of the power x. Over here, if we look at it, the power is a negative 2x. So that is a decay function. So that's how you can identify growth and decay just by looking at it. We're also going to graph it and we'll see what it looks like when it is a decay function. Okay? What is the domain of this? Well, domain is the limit, if there is one, on the x values you can plug in. Sometimes there's x values you plug in and it will make a graph undefined. For instance, if you try and plug something into the denominator of a function, and the value makes the denominator 0, that you can't use that x value. You would exclude that from the domain. In this case, we can plug in positive or negative numbers for x, and we'll get an output. It doesn't matter. So our domain for these are all real numbers. And in fact, for all these growth functions of base E and decay functions of base E, your domain should always be all real numbers, because there's no limit on what we can and can't plug in. Our range, on the other hand, is going to be different. There will be a limit, and it goes with the asymptote. If we think of standard form, it's very similar to standard form of other equations we looked at, but standard form would be y equals a times e to the x minus h plus k. This k value is our asymptote line. So we would say y equals k, which is the asymptote line. In these two functions, is there anything being added or subtracted from e to whatever power we have? And the answer is obviously no. So our asymptote line is y equals 0 for both of these. That is going to change when we go to the next slide. Okay? So the range, our graph is does our graph open up or open down? Well, it's the same thing with these. We have a positive a value. That means everything opens up. So our range is going to be all y greater than 0 for both. Not greater than or equal to, because the asymptote line is like in the invisible fence. You will not cross that invisible fence. You won't touch it. It's a border for the graph, so it keeps all values above or below it. So now we actually want to graph it. We need to get 3 points at least on our equation. Let's put that back. So let's graph the one on the left first. We're going to use our graphing calculator. Y equals 2 times e to the power of x. And let's just graph it to see what the picture looks like. Graph it. The window is off a little bit. So here is the graph. Change my window. I went to a more standard window. Here's what the graph looks like. You can see a growth function as I trace the actual graph. It starts out kind of flat and then it takes off. Growth function. Okay, it will continue in both directions forever and ever. It's hard to see. It doesn't cross this y equals 0, this asymptote line. Everything is above it. So we can see that that matches up with our rate. So if we have a hard time guessing is it above or below, you can update graph it first and see if the values are above or below the asymptote line. Okay, if I want 3 points to plot, I just go to my table, hit second table, and get some smaller values. I might put my table up here a little bit higher. Some more manageable values here. Ooh, too far. See if we can't. Mouse got a little bit. Pointer got a little bit out of control here. Here we go. So it looks like oh, there we go. Back to a little crazy there. Here's our table. So we can plot, pick some points to plot. 0, 2 seems to be a pretty obvious point right here. We can plot negative 1.73, that would be like right about here. 1.73. And we can plot 5.43, which would be like right about here. And there's points on the graph. Okay. Well, let's try the other one now. Let's try y equals e to the negative 2x. E to the negative 2x. That's not how it looks. Let's try that again. Don't know what happened there. Let's try this one second. E to the negative 2x. We've already assumed this is a decay function. It's the warning bell. We better get to work. Y equals e to the negative 2x. We graph this one. And you can see what the graph looks like here. Drag this one out. I can get a table of values. Pull the value out, or pull the table out. Shrink it down a little bit. Then we have another table values. We can plot points on there, and we can get any points we want. So that's graphing those in general. Okay, just to make sure that we know what to do when we have more x, or excuse me, more k or h values than we did in the last problem. Well, let's graph one of these functions, okay, with a more extended equation. So let's look at the first one. over here on the right. F of x equals e to the negative 1.5, x plus 2 minus 4. I guess this will be the second one. But the only one you can see is I've covered up the other problem. The domain in range. What did we say the domain was going to be for all of these? Well, I can plug in any value I want for x again. So this is going to be all real numbers. And our range, well, our range goes with the asymptote. Come back to that in a minute. How about growth or decay? Is this going to be growth or decay? Well, if I look and I were to distribute that negative 1.5 to x and 2, I would have a negative x value, which means it's decay. My asymptote line. My asymptote line is the k value. K is negative 4, so y equals negative 4. That's my boundary, so this graph is going to move down 4 units. Actually left 2, got that x plus 2 up there. And my range, if I look at the a value, a is positive. It's a positive number. So my range is all y greater than negative 4. Okay? So let's see if that matches up. Let's graph this equation. Y equals, see if we can get this to work a little more effectively this time. E to the negative 1.5 times x plus 2, and then minus, I think we got it, and we're going to graph, and I think everything matches up with what we said it was going to look like. We said it was going to be all real numbers. Our range, our values are above the asymptote line, y equals negative 4. So y is greater than negative 4. It is a decay function. It goes down from left to right. That's how you can also picture it. Growth versus decay. Decay goes down from left to right. The growth functions go up from left to right, as on the last one. And if we want 3 points to graph, we just look at the table. And we can get 3 points to graph from there. Okay. And I know it says that negative 4 is on there, but we know that it actually doesn't. The calculator is just rounding the values. It stops at negative 4. It will not actually equal it. It's just rounding it up. It's very close, but never touches that number. So that's graphing equations, both simple ones and ones with the more interesting h and k values. Okay, last thing I want to talk about in this section is the fact that the exponent rules are the same for e as they are for any other base. Even though e is a number, well, we learned about number 2, it works, the exponent rules work for them as well. So when we multiply two things of the same base, we add their exponents. So e to the 9 times e to the 6 will be 9 plus 6, or e to the 15th. If you don't believe me, you can plug e to the 9th times e to the 6th in your calculator, get that number, and plug e to the 15th in. It should be the same thing. Over here, 2 times 6 is 12. E to the 3rd, negative 3 times e to the 5th is e to the negative 3 plus 5, which is e to the 2, the 12e squared. If we're dividing, the same thing. We reduce the fraction. 60 divided by 12 is 5. E to the 8th over e to the 5th is e to the 8 minus 5, so we end up with 5e to the 3rd. Plug it in your calculator, you get a number, same thing. Here we have one we can't exactly plug in our calculator because there's an x, but we can use the power rules. We distribute that 3 to both terms inside. I get 2 to the 3rd power times e to the negative 4x times 3. That's 8 e to the negative 12x, or 8 over e to the 12x. And that's a negative power that goes down to the denominator. And lots of fun with that in chapter 5 and 6. Square roots. So we can square root 9, we can square root e to the 4th. Square root 9 is 3. Square rooting would be like e to the 4 over 2. 4 over 2 is just 3e squared. That's 3. And finally, the cube root of 8 times the cube root of e to the 12th. Well, the cube root of 8 in the calculator is just simply 2. E to the 12th, the cube root of that And this figure would be e to the 12 divided by 3, or 2e to the 4. So our power rules work for e as well, as using it as it is. Okay, wrapping up the lesson, the PERT formula as it was used or called when I was in high school, A equals P times E to the R times T, E R to be PERT. It's not just shampoo. Okay. You deposit $3,000 in an account which has 3.5% annual interest rate, which compounds continuously. How much will you have after 3 years? What is the key word in that story problem or that sentence? The key word for the compounding of interest is continuously. When you hear the word, I guess both words, compounds continuously, that tells us that we're using the PERT formula. Okay? Other interest compounding, you would use the compound interest formula or the general interest formula. For this one, if it's compounding continuously, we need E. So we identify A is the amount, P is the principal or the starting amount. So the principal in this case is $3,000 times E to the rate. The rate is 3.5%. Remember, we take that, divide it by 100 to get our decimal, 0.035, or just move the decimal 2 places to the left to convert it from a percent to a decimal. 2.5 times the rate or the time t. We want to know after 3 years. So if we just put our money in an account for 3 years, the compounds continuously at a rate of 3.5%, how much money will we have? Now we just go to our calculator, we kick back, let it do all the work. 3,000 times E to the power of 0.035 times 3. I hit enter. And I get $3,332 and some change. 13 cents. $332.13. How much money do we make in interest? Well, we made $332.13 in interest. So that's what the banks do. They have different interest formulas usually, but they pay you money to keep your money in an account. Same ways if you take a loan out for a house, you pay them interest, so they give you all the money up front. That's how interest works. If you're in a bank account or an investment, you get interest, you get money paid. If you borrow money, you pay interest, or you pay more than the initial. So, I think we hit our targets pretty well. I think we're able to graph with base E. I think we proved that the exponent properties are the same with base E, and we saw that you can use E for the PERT formula to calculate continuous interest. Have your notes ready to go for tomorrow. Good evening.